Good afternoon, everyone. My name is Feng Peihua from Jiaotong University, Shanxi Province in China. It is my honor to share my study to all of you about my study. My study is about discontinuous phenomenon in fluid dynamics. Specifically, our study is focused on nonlinear waves in incompressible boundary layer. Okay, let's start. The contents of this presentation about three parts. The first one is the flow field driven by the single plane wave with a constant amplitude. The second one is with an increasing amplitude, also a single plane waves. And the third one is we changed our driven waves with, to the double plane waves with different physics velocity. The first, let me introduce some the background of my study. Actually, when I talk about the turbulent uh, transition from the laminar to turbulence, usually there contain three stages in this transition process. The first one, the linear stage, and the nonlinear stage, and the last, the turbulence occurs. But before the turbulence occurs, we discovered that the nonlinear waves in the boundary layer, there is a very important phenomenon which is called the multiplication of specks, which is discovered in 1966 by some Russian scientists. And this contradicts the specks discovered in the boundary layer, we usually considered it as solitary waves, but in the experiments, we observed its multiplication of the profile of the waves. And when we determine it's a kind of the solitary wave, it will not change its profile, but the change of the profile actually exists. So how to solve this contradiction? And some scientists confirmed their governing equation of this kind of the phenomenon is the Benjamin-Ono equation, and we solve this equation by solving this Benjamin-Ono equation and adding some driving forces. This kind of the governing equation are derived from the triple deck structures theory, and the details of this um, derivation of this governing equation you can see the relative to papers, and and now we can directly to talk about our research because of the time limitation. We use the three kinds of the driven waves in this in this flow field. The first one is the traveling wave, and in the traveling wave, in the cases we found that the energy of the wave distributes in the parameter space in the discrete branches. When we change the amplitude of this amplitude of the driven waves or the phase speed of the driven waves. And we all find the hysteresis loops between the uh, every two energy branches. And when we focus on the profiles of the nonlinear waves in every branch of this nonlinear wave, and we've discovered that the spike of the nonlinear waves increased one by one when we jump from the lower branch to the higher branch. And this is an application of the observation in the experiments that the multiplication of the nonlinear waves. Uh, but how to understand this is this kind of the phenomenon which is called multiplication. We also derived the perturbed wave equation and use the theory of the stability analysis to confirm that this kind of the phenomenon can be explained by the saddle node bifurcation. The details of the derivation is neglected in this report, and we can talk about this detail later if you are interested in. Um, the second case is that we use this driven wave with with an increase in amplitude, and we discovered that the energy branch is also distributed in discrete branches. But we also observed that the wave energy jumped from the lower branch to the higher branch via a very complicated process. The process is illuminated by the flow field here, and we can observe that when the branch is here, and the phenomenon is much more complicated, more complicated. And we also use the stability analysis, and we discovered that actually when the transition from the lower branch to the higher branch, it actually involves all kinds of the perturbed oscillator systems. In the third case is that we driven this wave field by a very special kind of the cases, which is a pair of the plane waves with actually a standing wave and the traveling wave. The standing wave is the zero phase speed, and the traveling waves is denoted by the omega 2. And here in our study, omega 2 is the most important parameter here. And when we change the omega 2 from a smaller value to a higher value, and we discovered the very special phenomenon, which is the energy of the wave, or the wave system is become from the periodical case to the quasi-periodical motion, and at last it becomes to the chaotic motion when omega 2 equals 0.77. And what happened if we continue to increase this important parameter omega 2, and we also discovered the backward of this process from the chaotic to quasi periodic, and finally to periodic motion when omega 2 equals 0.9. Actually, when we increase the omega 2 continuously, we discovered the same process, completely the same process again and again. And after several or 5 times, the system will go back to the chaotic system and never go back to periodic cases. Actually, here, this process is also can be illuminated in the Poincare section, and the dot here denotes to the periodic motion, and the black dots and the blue dots and the red dots are the quasi-periodic motions in different parameters, and then at last we'll go into the chaotic motion. Here we introduce the kind of terminology is the Rueller-Takens to chaos, which is said the system, one way of the system goes into the chaotic station from a regular state. And it says that the system can enter the chaotic station via several hop applications. And the first hop applications can bring the system to the periodic motion, to quasi-periodic motion, and the second one bring the system to from the quasi-periodic motion to the chaotic state. But here, what we found is much more complicated than the Rayleigh-Takens routes to chaos, and we call it forward and backward RT routes to chaos, which means it goes to chaos and go back to the periodic motion, and it goes to chaotic motion again and go back to the periodic motion again. But at last, the system enters the chaotic motion finally. And this processes can also be illustrated by the spatial temporal wave patterns of these three different types of motions. And we can see that the periodic, quasi-periodic, and chaotic motions, the patterns of them are more and more complicated. The regular one to the more irregular one, and the last the complete chaotic one. And there is another very important phenomenon which is called intermittency in the wave energy, which means we also find this phenomenon the wave energies switch back and forth between the quasi-periodic motions and the chaotic motions in some specific parameters. Here, we provide a kind of the special technology or theory to explain this onset of the chaotic motion from the quasi-periodic motion by onset of singularity in torus, which means when the system goes switch back and forth between the quasi-periodic motion and the chaotic motions, actually its nature is the torus of the system is its go back and forth become thinner and fat to lead the onset and disappear of its disappearance of the singularity point. And this process can also be illustrated in the Poincare section in different time intervals. And actually here we prove this process numerically in Poincare section. And now I can give my conclusions of our study. The first one is the hysteresis loops consequence of the wave energy in parameter space exist when we change the very important parameter. And this phenomenon can be explained by the side node bifurcation in energy jump or fall. And then we also use the complex oscillator system as a very powerful tool for the stability analysis. And actually in this talk, we neglect the details of this process. And then the most important one is that we found the forward and the backward, the Rayleigh-Takens route to chaos, which is much more complicated than the traditional RT routes. And then we use the one special theory to explain the intermittency, to explain the onset of this the onset of the phenomenon, which is system is switch back and forth between the periodic states and the chaotic states. Okay, thank you. Thanks for your attention. Is there any questions?